Hello guys, how are you? I hope everything is absolutely right. And in this video, I'm going to discuss with the continuation of the topics which were earlier discussed by in the same channel, which is Introduction to Aerospace Engineering with the videos and the media. And in the last video, what we did the concept that was delivered was four forces of light, or the equations of motion. And for continuation of that, we just want to have the momentum. Now we're going to express the force in terms of momentum, and for that reason we have a momentum theorem. And in fluid mechanics, obviously we are talking in fluid mechanics, and let's see what we can have in terms of notes, in terms of expressions, in terms of pictorial representation or graphical representation, what we can have for the momentum theory. In momentum theory in fluid mechanics, it's the momentum theorem is a counterpart of Newton's second law of motion in solid mechanics. Okay, that is, you need to obviously this is the topic of a momentum theorem, is a topic of a fluid mechanics, which is the counterpart of Newton's second law of motion in solid mechanics. Definition is the sum of external forces or moments acting on a control surface and internal forces or moments acting on the fluid within the control surface produce a change in the flux of momentum or angular momentum through the surface, and instantaneous rate of change of momentum or angular momentum of the fluid particles within the control surface. This is how you're going to have this, because in this definition what we are dealing with are the external forces or moments, and which are acting on a control surface. That is the sum of external forces and the sum of the internal forces or moments normally acting on the control surface and on the fluid within the control surface, and that will eventually, for collective force will collective sum will produce a change in the flux of momentum, that is the angular momentum through the surface, and an instantaneous rate of change of momentum or angular momentum of the fluid particles within the control surface. So that is how a flux of momentum would be produced, calling an angular momentum, and through the surface, and which are going to produce an instantaneous rate of change of momentum or angular momentum of the fluid particles within the control surface. Mathematically, for linear motion of an inviscid fluid, the theorem can be expressed in vector notation by this. You have to express it in this vector notation, and actually providing it in a double derivative. Okay, there is this you need to actually know. Whenever there is a whenever there is a surface S that needs to be always taken as a derivative ds, there would be n available, which is the unit normal directed, which is as a unit normal directed outward from the surface. This is the unit normal directed outward. Whenever there is surface area, there is ds. Whenever there is ds, there is n. So we're going to have the double derivative. We're going to actually form it because of the surface area, and also because of the sum of two fluids. And also b, we're going to say that v is in the vector velocity vector. This v is the velocity vector, which generally depends on position and time. This velocity vector depends on position and time. That is why we have taken this. Okay, d over d, and this is because of the time, and this is the surface area, and this two are equal to what in the negative form? Plus b. Let's see what the b is. This is the expression for what? The momentum theorem. B represents the vector sum of all body forces within the control surface acting on the fluid. So B would be the sum of, where represents the vector sum of all body forces within the control surface acting on the fluid. Rho is the mass density of the fluid. Rho is the mass density of the fluid. You need to understand, define as the mass per unit volume. This is how you're going to define it. Rho is always present rho is, in case of this, when you're talking about this, rho is always present. Okay, rho is the mass density of the fluid defined as the mass per unit volume. For the angular momentum, obviously because of this forces, or the collection of the forces, external and internal forces, there will be an angular momentum as well generated, and that will be Q is equal to this, which is rho into V into R into V into N into ds plus d over dt into V into this and this, which is rho into V into R into d of t. That is how you're going to explain it for the angular momentum. This is how you're going to explain, which is the surface area rho V into R and V into N ds plus d into t, and V this, which is equal to this one. Okay, and dt, this is how it has been explained for the angular momentum. Here Q is the vector sum of all moments, both internal and external, acting on the control surface or the fluid within the surface. R is the radius vector to a fluid particle. R is the radius vector to a fluid particle. Okay, and Q is the vector sum of all moments. Q is the vector sum of all moments. That is the vector sum of all moments, both internal and acting on the control surface or the fluid obviously within the surface. R is the radius vector to a fluid particle. R is a radius vector to a fluid particle. That is how you're going to do it. So this nozzle, obviously we have actually expressing it pressure distribution on the wall. This is the wall, this is the pressure distribution on the wall. Okay, and this is the control surface outside, just on this outside the lining, you can say. And this is the nozzle, a jet of water impacting on the wall. This is the jet of water impacting on the wall. So this is how the pressure has been distributed, and the distribution on the wall is also being represented. Okay, so this is how you're going to show it, which is the P is rho is the mass density of the fluid defined as the mass per unit volume. For the angular momentum, this would be this one. So what we have learned, that what we have derived from the last equation, that was the combination of time and obviously the combination of the surface area. And when we actually time and depends upon the position, obviously depends upon the position and time, we express it in negative form plus b. B represents the vector sum of all the forces within the control surface acting on the fluid. So that is how you're going to express it for the angular momentum. Now this had been replaced by this vector in the vector form. And Q is the vector sum of all moments, both internal and external, acting on the control surface or the fluid within the surface. R is the radius vector to a fluid particle. Okay, this is the control surface. So nozzle diameter is what? 10 centimeter. Just giving an example, because of that expression, nozzle diameter is 10 centimeter. Water velocity from nozzle is 60 meter per second. That is the velocity of the water from the nozzle, and mass density of water is approximately 1000 kilogram per meter cube. And equation will be written in x direction. That will be the equation that will be written in x direction. Also B is equal to 0. Since control surface does not enclose any bodies, there you know that the nozzle diameter is 10 centimeter. Water velocity from the nozzle is 60 meter per second. Mass density of water approximately is 1000 kilometer per cubic meter. An equation will be written in x direction. Also B, which is the sum of all the forces equal to 0, since control surface does not enclose any bodies. So that is how B would be 0. This negative expression would be equal to this. Okay, this is how you're going to explain it, which is obviously is the equivalent. We have removed the time factor, we have removed the b, okay, or the b vector. So that would be the, we're just going to apply these values obviously at the end of at the end, when we have the more simplified form of this, and we're going to explain it later on. Let's see, measuring P relative to the atmospheric static pressure P. Static pressure P is 0 everywhere, okay, along the control surface except at the wall. Pressure, we have actually informed about the distribution of the pressure about the wall, okay. Here N is directed to the right. Here N is directed to the right, so that the surface integral on the left becomes the total force exerted on the fluid by the pressure on the wall. If F represents the magnitude of the total force on wall, that would be I into F, that would be S into S of PV into V into N into D of S, okay. This is how you're going to express it. And for the fluid entering the control surface on left, that would be V is equal to 60. These are the numerical values you can actually put in. And when you have this, for the fluid leaving the control surface, the unit normal to the cylindrical surface has no component or x direction, hence that would be this minus 36 into 10 raised to 5, which is a iota, and this is also the form which is of ds. The surface integral reduces to the nozzle area of this, okay. Thus, without actual determining the pressure distribution on the wall, the total force on the wall is found from the momentum theorem to equal that one, which is in kilonewton, sorry. So this expression of the momentum theorem help us to get the distribution of the pressure as well on the wall, and also it help us to find the for the fluid leaving the control surface, a unit normal to this cylindrical surface has no component at x direction, okay. So that is how you're going to see it. So this is whole concept of actually dealing with the momentum theorem. We have learned about the expression in terms of what the mathematical expression in terms of position and time, and we also learned about the definition, the angular momentum, instantaneous rate of momentum, and we have discussed about when there's an instantaneous rate of momentum, there always will be a time involved, and it is all about these forces, some of the forces internal and external on the control surface and also on the fluid within the control surface. That is how it's going to actually impact the pressure on the wall, and that will create a distribution. And we have learned from our actually for this expression. If you want to have the proof of this expression, you can let us know in the comment section. We will actually provide you a separate video from which you can learn that how this expression has been have actually taken such a shape by providing you the proof as well, so that you can learn that yes, it is also from this from some solid basis and solid source, so that you can learn about this equation or mathematical expression as well. So we have also learned about the symbolic representations of different letters in this equation, and you can also learn about that. And also we have learned about the representation of the vector sum of all body forces in the control surface acting on the fluid. Rho is the mass density of the fluid defined as the mass per unit volume. For the angular momentum, that would be this one, okay, and which is like yes, for the angular momentum there has to be a you can say a triple derivative, okay, a combination of a triple derivative in terms of time, and also there is always a surface derivative, a double surface derivative when you're talking about the radius and also talking about the velocity. Here Q is the vector sum of all moments, both internal and external, acting on the control surface or the fluid within the surface. R is the radius vector to a fluid particle, okay. This is how you're going to explain all the things in detail. So we have driven this from that, from this actually diameter and the velocity, and also the mass density of water, which is approximately 1000 kilometer. You have just putting out the value on this, measuring P relative to the atmospheric static pressure. P is 0 everywhere along the control surface except at the wall. Here N is directed to the right, so that the surface integral on the left becomes the total surface exerted on the fluid by the pressure on the wall. If F represents the magnitude of the total force on wall, this is known as this. And for the fluid entering the control surface on left, for the fluid entering the control surface on left, that would be this one. For the fluid entering the control surface on left, that would be 60 iota, and that vector form will be minus iota. Just putting it 60 iota minus 60. Okay, so that will give us what? Multiply by 1000. That is the velocity. Velocity is 60. Okay, and pressure or the mass density is also 1000, and velocity again multiplying by giving this equation, which is 1000 into 60 into 60, and n is minus iota. Just putting out the values, you give out the expression like this. Okay, but obviously you know that you need to solve that for F as well, and iota, if this is iota of IF, because this whole equation has now been replaced by this whole is now being replaced by iota of iota F, and we have actually learned because of the force exerted on the fluid by the pressure on the wall. So that F represents the magnitude of the total force on wall. That is that magnitude. That is how it has been shown like this. Because of the pressure, there is a force exerted on the wall, and for the fluid entering the control surface on left, that is how you're going to show it. And I hope that is enough for the video. That is actually hoping to explaining it in terms of the magnitude as well, explaining in terms of the forces, just multiplying it, putting in the force, and have this one. And also you're going to have this one, which is this area surface 78 point this. Thus, without actually determining the pressure distribution on the wall, the total force on the wall is found from the momentum theorem to equal, that will be 28.3 kilo Newton. Okay, that is how you're going to see this one. And I hope that is fine enough. If it's okay, you can actually let me know in the comment section, and if it's perfectly okay, you can let me know. Let's see, with the coming videos we're going to explain further concepts, further expressions. Let's see what we can have, and I hope that you're going to actually help us understand better as well. Till then, take care and have a nice day.